Oh. Sure.
All right. Let's do it. Okay. I'd like to welcome our colleague Steve Collins from Mechanical Engineering. He's going to be talking to us about the $6 million man at some level. He has a long history of work in robotics and in human motor control. So without further ado, here's Steve.
Thanks, Chris. Hey, a lot of familiar faces. I like action movies. I'll admit it. But I hate the way biomechatronic devices are portrayed in them. And it's not just that they routinely violate the laws of physics. One of my favorite examples of which is it's not touching the ground with your skin that kills you. It's the acceleration, right? Full speed, bam, yay, no problem, right? And it's not that they set the bar really high. I think it's great to be striving for greatness. What drives me crazy is that they make it look easy, right? All you need is some money, a little free time, a knack for fixing up old cars, and boom, super suit, right? And the reality is that big teams of very smart, talented people have invested heavily in resources over the last few decades into these kinds of problems. And yet, along almost every dimension, we have a long ways to go before we even match healthy human performance, let alone augment it, right? And the question I want you to ask yourself right now is, why? What is hard about this? What are the real challenges? What are the keys? If we solved something, would everything get easier? And the second question that's kind of a corollary is, if I gave you a big pile of money and a talented team and 5 years and I said, go out and make real progress in this field, build a foundation for future work, what would you do? What kind of processes should we go through that have a high probability of success and make lasting impact? And I'm going to argue that what we do in that exact scenario is ineffective and inefficient. And I think is partly responsible for our slow progress. And I'm going to propose an alternate process that I think has better potential. And I think the best way to make this case is to take you along the path that I've taken to coming to this conclusion. And it starts a long time ago, in time with poor graphics, in a lab where we were using very simple models of locomotion to try to understand robot walking. And this is arguably the simplest model of walking. We have a point mass representing the body. We've got inextensible legs with negligible mass. There's gravity, there's a ground, and we have cyclic stepping, right? And in this very simple model, we can make some statements about energy use. First, the best thing to do during the middle of the step is nothing. Vault up and over your stance leg like a pendulum. But at the transition between steps, you have to redirect your center mass velocity. And if you do nothing, your leading leg will land, you'll have a collision, you'll dissipate a bunch of energy. And since this is a steady state behavior, every joule of energy that you dissipate has to be resupplied at some point in the gait cycle. It turns out the most efficient way to do that in these simple models is by push-off of the trailing leg, because that partially redirects the center mass velocity and thereby reduces the collision and the overall mechanical energy requirements. So inspired by these models, we wanted to build more efficient walking robots. At the time, and actually to this day, most walking machines use an order of magnitude or many orders of magnitude more energy to get from A to B than a human. And coincidentally, almost no walking machines embody any of these principles. So we designed a machine that does, and it looks like this. It's mostly passive. There's a hip with no actuation or control, knees that have almost no actuation, but little latches to keep them from buckling during the middle of the stance phase. And all of the energy is supplied at the ankle, once per step, through trailing leg push-off. Oh, can I get here? Yeah. And you can see that best here. So you see, just as the leading leg is about to land, the trailing ankle will move a little bit. And that's it. That's how we inject energy into the system. And using these strategies, we're able to match the cost of transport of human walking. This is cost of transport, that's energy used per unit distance traveled and unit weight. And you can see our machine had a similar value to that of humans and 15 times lower value than Osimo. And at the time, that was the most efficient walking robot in the world. So we were very excited about this result. And I was especially excited because I thought maybe we could take this and use it in devices that directly assist humans. But first, let's take a look at natural human walking and see if any of these ideas are relevant. And humans are very complicated, right? We're a big pile of cells with hundreds of muscles, and each muscle has lots of fibers, and there are all these neurons, and a very complicated thing. So we use a couple of abstractions to try to understand the mechanics of gait from a mechanical engineering perspective. And one is to look at center of mass work. So if we consider the center mass of the body and everything between the center mass and the contact of the ground as a leg, then we can get a rough understanding of the work done by that system by taking the dot product of the velocity of the center mass with the ground reaction force. And when you do that for each leg individually, you get curves that look like this. And I'm going to show lots of curves where we have time on the x-axis, here normalized to percent stride. Typically, these will begin with heel strike of the leg that we're looking at, and 100% will be heel strike of the same leg, the subsequent heel strike. And if we look at the work performed by this effective leg, you get this initial negative work phase and some stuff in the middle that I want you to ignore, and this big positive work phase at the end of the step. And looking at this through the prism of our simple models, we see maybe you can think of this thing as being that trailing leg push-off, and it happens just about the same time, a little bit before this other thing, this negative work phase, by the leading leg, which maybe we think of as collision. So perhaps these ideas are relevant to human walking. Another way to look at mechanics of gait in humans is to consider the body as a set of rigid links and look at the work done at joints, using inverse dynamics analysis, for example. And when we do this and look at the joints of the lower limbs, one joint in particular seems to account for most of that push-off, and that is the trailing ankle. So we wanted to see if there was a population where we could apply these ideas and maybe improve performance. And something that jumped right out of the literature is people with lower limb amputation. So when you have part of your leg removed, you typically are fitted with one of these conventional passive elastic prostheses. And these devices result in a big decrease in trailing ankle push-off. Our models suggest that that should increase the overall mechanical requirements to walk. And coincidentally, people with lower limb amputation tend to have at least a 20%, 10 to 20% increase in metabolic cost to walk. And metabolic cost is a measure of the biochemical energy used in your muscles to do things like move around or, keep your heart beating. Now, 20% might not sound like a lot at first, but that's about equivalent to wearing a backpack with 20% of your body mass in it all the time. In my case, like a 35 to 40 pound, depending on the time of the year and so on, backpack wherever you go. And I mean, a lot of times I will avoid carrying my 3-pound laptop across campus, right? So 20%, that's a very big, meaningful change. So we thought, if we increase that trailing leg push-off, can we make it easier for people with amputation to walk? And one way to do that would be to take a big motor and battery and stick it on the ankle and just drive that push-off phase, right? But we noticed that the energy dissipated during this collision is of a similar magnitude to the energy required for push-off. We thought, well, maybe we can capture some of that energy that's normally dissipated and recycle it usefully for push-off. So we designed this very specialized prosthesis to do just that. And you can see right at heel strike, this big spring here is compressed. It stores a lot of energy. That energy is locked in place. Now later, a separate latch releases, and then the spring, okay, spring is compressed, locked in place. Later in the step, a separate latch releases the toe. The toe vaults forward, and all that energy is returned to the person's body. Right? And using onboard sensors, we could tell that we are indeed capturing and returning energy as we had wanted, which is cool. But does it provide the expected benefit to human users? Well, the only way to figure that out is to perform an experiment on people, and that's what we did. So we collected some pretty typical biomechanics measures. We had people walk on an instrumented treadmill that measures their ground reaction forces. We measured the positions of their body segments using a motion tracking camera. We measured the oxygen and carbon dioxide that they consume with this by sampling the gases that they breathe. And this is what that looks like in hardware. And we considered 3 different conditions. First, we had people who are not amputees participate in the study, and we simulated amputation in some conditions by locking out their ankle joint with a simulator boot that has a little attachment on the bottom to which we can attach different prosthetic feet. We compared biomechanics outcomes while people walked in their street shoes, while they walked with one of these conventional prosthetic feet, and while they walked with the energy recycling device. And as expected, when walking with the conventional foot, ankle push-off work was reduced, and center of mass push-off work was also reduced. The energy recycling foot captured energy that would be normally dissipated, then returned it, which resulted in increased ankle push-off and increased center of mass push-off. And at the same time, we observed the energy penalty for walking with simulated amputation was reduced. So this is the energy cost for walking in street shoes. When people put on the simulator boot and conventional prosthesis, energy cost went up by about 23%. With the energy recycling foot, energy cost was only 14% higher. So you could say it's a 10% reduction in energy cost. Whew. So from a very simple model to a robot, to the design of a device, to an experiment on people, just a single linear track, same idea, goes through, it works. Beautiful. We're happy. All done. You can just wash your hands, walk away. Everything's good. Except. And this is the crux of the talk. If you take nothing else away from the talk, I hope you take the next few minutes away. When we took this same device and tested it on people with amputation, we found the opposite result. Right? With the simulator boot, benefit, 10%. People with transtibial amputation, a detriment of 7% in energy cost. Why? Why? Is it something about the design? Was it something about training? I don't know. I still don't know. And what really drives me crazy is that I can't reasonably find out. The design of this device took 5 years before it was robust enough to withstand the about 100 hours of testing and training required to get the outcomes that we care about. Any change that I want to make to that device takes, optimistically, months, and realistically on the order of a year to implement and refine and get it robust enough to test, right? And that leads me to my first point, which is specialized devices like this one are not good experimental tools. They do one thing really well, and they strongly limit the types of experiments you can do. One of the factors that we think might have been important in these experiments is the shape, the effective rollover shape of the foot. And as we were refining our energy recycling foot, we discovered that if we put little pieces of foam on the bottom, it felt a lot easier to walk on the device. And later on, we actually did a separate experiment where we systematically varied rollover shape in a controlled way and found that if that can make a very big difference, 50% change in energy cost or more. And we didn't think when we set off on this that those kind of factors would be important. And that illustrates an important point. People are so complicated and unpredictable that very subtle factors can be really important, things that you wouldn't expect. And it also illustrates that as we're designing and refining these specialized devices, secretly we were performing an optimization, but we didn't realize that the thing we were changing was important. And we probably did this in lots of ways, right? There are all kinds of choices that you have to make in the design of these devices that we didn't think of as being most important, but may have had a strong impact on results. And that leads me to a third observation, which is that when you perform an experiment that is an A-B comparison, this complex device versus that complex device, and there's a change in some performance measure, we really wanted to say the reason for the change in energy cost was the energy recyclingness of the energy recycling foot, right? But maybe it had something to do, it was nothing to do with that, and it was about stiffness of the keel or stiffness of the spring or rollover shape or something, right? So if we look back over this, which is a very typical example of the development process used in biomechatronics right now, and look at the tools available to us, here's how I would assess them. What good are simple models in intuition? Well, we need them, right? You need them to develop hypotheses, to inspire designs, and to help you interpret results of experiments. But they are not good enough to lead you to the design of an effective device. Similarly, eventually, we need really specialized devices. We need products, right? That's the end game here. We want somebody to take a device out into the world and have improved performance. But early on in the process, these are not good experimental tools because they restrict the type of early stage experiments that you can perform. And importantly, these should not be A versus B, one little point and another little point in the design space. But maybe we want to do things where we take a functionality or a parameter that we think is important and vary it and characterize response with respect to that one parameter. Which brings me back to the very beginning. What is the challenge? What is hard about developing these devices? I would argue it is not how to design specialized robots, right? Over the last several decades, we've gotten really good at making machines that meet design requirements, right? We've got CAD tools, we've got finite element analysis, we've got dynamics simulation software. All that stuff helps us to make very good predictions about whether something is going to work or fail. And we're very creative and good at these problems. We like these problems. But that is not the real challenge. The real challenge is predicting how the human will respond to forceful interactions with these devices. And that's where we don't really know what's going to happen. Or another way of putting it is the Tony Stark problem, right? As roboticists, we get really geeked about the tech side, how to make the thing do what we want. But we haven't asked what functionality we should be using. We haven't answered that question adequately yet. And that's what our research is seeking to address. And I think the way to do this is what I like to call human-in-the-loop design. So get to experiments with people as fast as possible because that's where all the new information comes in. Close the loop as soon as possible. And try to decouple the functionality that you're testing from the design of a specialized device so that every time you change something, it doesn't require years of development. And finally, instead of doing little data points, try to quantify design relationships. And the tool that we think enables this approach is something we call a universal device emulator. It's like virtual reality for your leg. It's a haptic interface. So you put it on the body, and it pretends to be some proposed wearable robot design. And then you can evaluate that, and you can change aspects of it in a controlled way and see how people respond. And so we built some of these. And here's one. And this is a universal ankle-foot prosthesis emulator. And it has three main components. First, there is a lightweight end effector worn on the body. Second, we have a tether that connects to very powerful, capable off-board motor, actuation, and control hardware. And this is what it looks like in our laboratory that I share with Hartmut Geyer down in the basement of Wien. This is our 2 kilowatt AC servo motor, weighing in at 15 kilograms. Lots of power, right? And you can see the tether and stuff a little bit better in this picture. Here we have a Bowden cable coming in. That's how we transmit mechanical power. And this instrument end effector, I guess this is the person walking with here is a unilateral transsepal amputee. You can see the end effector a little better if we slow things down. It has one axis joint. We sense the position. We sense the torque using, here we have a spring and we measure the position of both ends and calibrate that measurement. And a series elastic element which helps us to achieve good torque control. Now I claim that this is going to enable us to be versatile and high performance, and here's the proof. We've done some benchtop tests and found that, yeah, we can measure the torque really accurately. We can change the torque very fast. So this is a step response, a rise time of about 60 milliseconds, going from 0 newton meters to 175 newton meters. And for the uninitiated, a typical peak torque during walking at the ankle is like 100 to 120 newton meters. So that's a big torque. And one of the keys in haptic interface is the closed loop torque bandwidth. That provides a limit on the fidelity with which you can emulate different dynamic elements in the design. And here we have a bandwidth about 17 hertz. The whole thing, the part that you wear in your body, weighs less than 1 kilogram. And if we have a person walk using some control algorithm that I'll explain a little bit more later, we see that there's a good match between the measured torque, which is the blue line, and the desired torque, which is the black dashed line. If you look at it either in time domain or in this angle torque domain, with a torque error of about 3 newton meters RMS. Taken individually, any of these outcomes is at least twice as good, well, significantly better than any other prosthesis or exoskeleton for the lower limbs to date. And when you look at the set of outcomes, we're typically an order of magnitude better and at least one than everything else. And that's not because we're, the cleverest mechanical design people, although, we're not bad at that. But it's because if you exploit the laboratory setting, give up on autonomy, stop trying to pretend to be a product, and embrace the fact that this is an experimental tool, things get a lot easier. Now, why should you care about this? Why is this cool? Number one, you can go from an idea for an assistive device to a test on a person in hours, not years. So many orders of magnitude reduction in the time. You don't have to be good at building stuff. And I say this in a room with lots of computer science people. All you have to do is to be able to code a little bit, and the device will express your ideas. If you are a builder, it's way easier to design these end effectors than an integrated system, right? We've taken you don't have to have control on board, you don't have to have energy on board, you don't have to have actuation on board. Everything, once that part of the system is solved, all you need is some mechanical structure that supports and moves around and a little bit of sensing, right? And these are a couple of end effectors that we're currently using. This is an ankle exoskeleton, and this is a 2-degree of freedom prosthesis that does both plantar flexion and inversion, eversion, or pitch and roll, if you like. And we're really excited about these platforms for not only research, but as potentially commercial tools for a clinical setting, where you can imagine with the right interface, a person could use these to express to a potential user of a robotic prosthesis or exoskeleton a few different devices that are available on the market so they can try them before they're prescribed. And you could even, say, tune parameters for those devices and have the person experience it before it's built. And to give you a point of reference, the Biome, which is maybe the most advanced prosthetic ankle on the market, costs over $100,000. So before you mortgage your house, you want to make sure that this thing is going to be effective for you. Now, we're also, of course, interested in using this as a research platform. And I'm going to tell you about a few experiments that we've been doing, one in a lot of detail, and then I'm going to touch on a few other experiments that we've been performing in our lab. And the first is about ankle push-off work. So let's come back to this idea of augmenting push-off. We think it's important, and we think that maybe more work done by the ankle is better in terms of energy cost for the person. But more work also implies a heavier motor and batteries, which we think is bad for performance of the person. So in order to make a rational decision in the design of an autonomous robotic ankle, we need to have a quantitative, we need to quantify the benefits of more work so we can weigh them against the costs of bigger motors. And no one has done this in isolation before. So we set out to try. And we designed a controller that's well suited to perform this experiment. It operates in joint angle versus torque space. If you take normal ankle function and project it into the space, you get curves that look like this gray line. During most of the step, you have this dorsiflexion curve where the ankle is, your toes are getting closer to your knee, and torque is increasing. And then at the end of the step, you have this plantar flexion phase, and torque is decreasing. And this is a displacement force space, so area under the curve is work, and the area inside the loop is the net work over the course of a cycle. We call it a work loop. So we approximated this with a couple of piecewise linear functions, and then maintained this dorsiflexion phase consistent across conditions. So that means during most of the step, the behavior of the device is the same, and then just varied these plantar flexion curves. And what you get is a big range of net work production or absorption by the device across conditions. And so you notice that we have this one parameter that we think is interesting, and we're varying it over a big range, and that's the only thing that's changing. Nothing else in the system is changing, which is, we think, important for good experimental design in this domain. So we did that. We had 10 people walk, and here's what we found. First of all, we are able to vary the net work provided by the device over a big range, up to values approaching 4 times that of the biological ankle, so big range. This is, just to give you another perspective, this is power at the ankle joint, and you can see we're getting more than 2 times the peak power, so half a kilowatt at the ankle joint is lots of power. And we measure metabolic rate, we're able to create this figure. And this is the key figure. This is the kind of figure that I would like to see lots of groups produce. This is, this is it. This is the thing that we think matters, the thing that we think, the functionality that we think gives some benefit, and the benefit that we think can be achieved with it, right? In our case, the net prosthesis power on the x-axis and the net metabolic rate on the y-axis. If we put in the data from 10 subjects, and each set of colors corresponds to a different individual, we see that, as we kind of expected, increasing push-off tends to decrease the user's energy cost, which is cool. There are a couple of landmarks in this space that are interesting. The first is a line with a slope of -4, which is what we might expect if every joule of the device, every joule of work performed by the device exactly replaces 1 joule of mechanical work performed by muscles in the person's body. That's because muscles have an efficiency of about 25%. And you can see for some subjects, they're pretty close to operating along this line. But on average, there tended to be a diminishing return as we increased device work. And this is an exponential fit to that curve. Interestingly, energy cost of the user tended to continue to go down even as prosthesis power got way bigger than what you observe in the biological ankle. So many people have an intuition that the best thing we can do with a robotic device is exactly imitate what the biological system does, right? Now, what exactly that means, if you start to really parse it, becomes ill-defined most of the time. But even in this particular outcome measure, we see that, so normal walking is somewhere in here. Clearly, more work by the device is better. And if you reflect on it, maybe that makes sense, because the cost structure is different, right? You pay for more work by the device, but you pay for it in a different way than you pay for your work performed by your own muscles. Another thing that jumps out for me in this plot is the scatter. And some people really benefited from a lot of work, and some people actually had a minimum cost for less than the peak value provided. And that underlines the importance of individualized or tailored device design. But notice that we're now able to start to have a conversation about trade-offs in these designs. If we want to say, if we propose putting out 0.2 watts per kilogram with the device, and we think about the motor and the battery that would be required, we can see whether that would be a net benefit to the user, which is great. If we dig a little deeper, we can start to see the mechanics that might be responsible for those changes in whole body energy cost. This is one example. This is the hip joint power. And you can see that as device push-off work is increased, the positive work performed by the hip on the prosthesis side is decreased, especially during the phase right during and after push-off. And this is cool because if we just had maybe this cyan line and this gray line, it might not be so clear exactly what is changing as you increase that push-off. But because we do a nice big parameter sweep, these trends are very salient and obvious. And right now this is all data from experiments with simulator boot, and we are repeating the experiment with amputees. I think we have 5 subjects enrolled and 1 subject who's completed the protocol. And the results are very interesting. But you won't hear about them today. Okay, so that sort of wraps up the experiment I want to talk about in detail. And now I'd like to touch on a bunch of other little factors that we think are interesting. One is the timing of push-off. So the amount of work in push-off is important. The same models that predict that also suggest that the timing of push-off is important. But it's very hard to change the timing of the onset of positive power at a joint independently from the magnitude of work performed at that joint. And this has confounded lots of other experiments that tried to get at these ideas. Fortunately, when you have a 2 kilowatt AC servo motor, you can just make the joint do whatever you want, whenever you want. And that's what we did. We forced positive work onsets at very early and very late times during the gait cycle, and found that it does matter. Timing matters, which we expected. And in fact, with poor timing, the effect is as if you provided no work augmentation at all. That is to say, you're just throwing the energy away with no benefit to the user. And with optimal timing, you can get a substantive benefit, which is cool. In fact, with really bad timing parameters, people have a very hard time walking. Now, all these results so far have been for prosthetic devices. We're also interested in exoskeletons. And perhaps counterintuitively, exoskeletons offer a wider range of assistance approaches because the device operates in parallel with the person's joint, and so you can let the person bear some of the burden of moving the leg around, right? One of the things that people have often suggested in the literature as a way of assisting and improving performance during locomotion with an exoskeleton is to provide a torque at the joint that's similar to the torque normally produced by the biological tissues at the joint, but perhaps scaled down, so a scaled version of the same torque pattern at that joint. And this, seems reasonable as a first guess, right? But we have recently completed a test of this idea that suggests that actually it's not very effective. And perhaps counterintuitively, as we scaled up that average torque at the joint following a similar pattern, energy cost of the user increased. Somehow we're interfering with gait instead of assisting it with this kind of approach. And it might have to do with mechanics at the muscle fascicle level, which we're starting to investigate. These are hot off the presses. I don't know the answer yet. But it may have to do with actually, counterintuitively, you can increase the work requirements of a muscle fascicle by decreasing the torque at the joint. And the reason is that muscles are in series with tendons, typically. So if a person has tuned their gait so that the muscle fibers remain isometric most of the time, and mostly the tendon just stretches, they mostly bounce, and then all of a sudden you reduce the amount of torque at that joint, now to follow similar kinematics, the muscle fibers have to move a bit, right? And if they were moving 0 at first, and now they move a little bit, even though the force has gone down, the work done by muscle fibers can go up. So we're curious about whether or not that's the case, and we're looking into it. Of course, providing work augmentation at the ankle has a similar effect with an exoskeleton as it does with a prosthesis. But what's interesting in this figure are these 6 data points right here. So the y-axis here is metabolic rate compared to the cost of normal walking in street shoes. When you put on the device and turn it off and have it completely passive, energy cost goes up. This is something that's observed over and over again with these kinds of devices. There's a little bit of mass added to the leg, you restrict motion of the joint a little bit, and maybe there's some envelope issues that interfere with the way you'd like to move your limbs. And many people have demonstrated that with appropriate actuation, you can do better than the penalty for wearing the passive device. But what before last year had never been demonstrated was doing so well that you more than make up for that penalty and actually improve over normal walking. It's the so-called normal barrier of energy cost during locomotion has only recently been broken, and we are one of 3 groups that have done this in the last 12 months. One is in Ghent, one is another top-tier US university that hasn't published their results yet. So we're pretty excited about this. Now, in some pilot work that preceded this parameter sweep, we found that we could reduce energy costs below normal levels by up to 20%. So we then improved our controller a little bit and performed the bigger study on 10 subjects. And the assistance controller seems like almost the same, just a little bit easier to learn. However, the benefit somehow has been reduced or eliminated for some subjects. And so, that's not what you want as an engineer, right? But as a scientist, it's interesting. And we're beginning to probe this and try to understand what are the factors that aren't obvious when you first look at the intervention, but actually have a big impact on performance. And I'm confident that sooner or later we're going to figure it out. And our calculations suggest that this can be translated into an autonomous device that still has a net benefit during walking. And we think that'll be cool for, say, elderly individuals who have trouble getting around. And whenever I say this, somebody usually during the question session will raise their hand and say, wait, you're trying to make it easier for people to walk? Don't we have an obesity epidemic in this country? Shouldn't we be making it harder so people get more exercise? And implicit in that question is the idea that if we make each step a little easier, that people will get a little bit less exercise from walking over the course of a day or a week. Now, I think that's a perfectly good hypothesis. I happen to have the opposite hypothesis. I think that if you make walking a little bit harder, people avoid it so much that the net effect is less exercise from walking activities over the course of a week. And we are currently testing that idea. We have an experiment where we send people out into the world wearing shoes that are carefully instrumented so that we can really accurately track how fast they're walking and at what uphill or downhill slopes. And then we can bring them into the laboratory. We perform a parameter sweep on a treadmill, and then we can attribute metabolic rate with each step, or metabolic energy cost to each step that they've taken. And we have two conditions, one where their energy cost is about normal, and one where the energy cost is increased by about 15%. And there are a couple of interesting things that have fallen out. We're very early stages, but first is getting people to complete the protocol has been a bear. We've had an incredible dropout rate, and even the experimenters have refused themselves to complete a 2-week trial wearing the device that increases energy cost a little bit. In the one subject, and so we've been gradually stepping down the penalty to try to get compliance with the protocol. And in the one person that we've had complete it, the result was shocking, and I don't know if I even believe it. It was a 3-fold reduction in the number of steps taken over 2 weeks. 3-fold, 10% increase in energy cost, 3 times less steps. Crazy, right? So stay tuned, more to come on that. Now, another kind of fun thing that you can do when you start to manipulate energy cost is manipulate it selectively to try to reinforce desirable behaviors as, for instance, part of a rehabilitation regime. So during rehab, you come in, and typically a clinician tries to use social pressure to convince you that you should really work harder and use the paretic limb more. And it's hard and it sucks, but if they're a nice person and you want to make them happy, then maybe you do, or you're really motivated to get better. We think it would be really cool if you could change things around so that instead of the easiest behavior corresponding to a long-term poor gait strategy, that it could correspond to some desirable behavior that will in the long term improve performance. And unfortunately, I don't have enough time to explain this in such a way that you'll actually understand it. It's a little complicated. I apologize for that. But we're interested in these kinds of problems. And so far, our results are a little bit mixed. We see that sometimes people adjust their behavior as we want, and sometimes they don't. And there are very complex adaptation dynamics involved, and we're starting to probe those things. Hopefully, the results will someday have an impact on patients who've had a stroke. Okay, so that's a lot about energy cost. What about stability? Balance. Balance also matters. And every time I show that figure with the cost of transport bars, I have a pact with myself that I must show this video of this very efficient but extremely marginally stable robot falling down. However, the same group has recently produced a robot that is both very efficient and very stable. This is the Cornell Ranger. Our own Pranav Bonsul. Is Pranav here? Not right now. Was a key member of this team. And this machine recently walked 60 kilometers, setting the distance record for robot walking. And it's a planar machine, which helps a little bit. But the control algorithm that keeps it stable is that it looks at its state once per step, and it decides two things. Okay, first, how far of a step I'm going to take during the next stride, and how much am I going to push off with my trailing leg during that period. So we've been thinking about these kinds of control strategies and wondering if we can apply them to, say, prostheses to improve stability for amputees. Now, humans are three-dimensional creatures, so we can't exactly translate the Ranger control algorithm. We had to develop some of our own, and we used a 3D model to do this. And here we have the machine walking on uneven ground. The robot doesn't know what the floor height will be on the next step, and this presents a disturbance. And what we wanted to know is what kind of control inputs are most effective at recovering from these disturbances. Everybody knows that foot placement is important in these 3D models of walking. But what if you can't control foot placement? If we have only access to the ankle of a person with amputation, can we do any good just by modulating torques or works at the ankle joint? So we looked at a bunch of different control inputs. Again, changing something just once per step, either step width or step length, or the combination of the two, or doing ZMP-like center of pressure modulation of the stance foot, or modulating the amount of work delivered by the trailing leg during push-off. And what we found, to our surprise in these simulations, is that actually, under most disturbance conditions, modulating trailing ankle push-off is the most effective at recovering from these random disturbances. You can tolerate so these are the different control inputs, and this is for modulating trailing ankle push-off. And this is for the combination of everything, with the y-axis here being the magnitude of the random disturbance. Well, this gave us some hope, and we thought maybe we can translate this into a controller for hardware that really helps people with amputation. And these, again, are results hot off the presses, just in the last week. We found that, yeah, we can. So first we extracted a simplified version of the controller that only uses a couple of states, mostly having to do with the side-to-side position and velocity of the center mass of the person, which we're capturing using cameras. We found that if we apply a closed-loop feedback gain that our simulation suggests should be stabilizing, energy cost goes down. If we apply the opposite gain, energy cost goes up. Everything else is the same. The average behavior across conditions is the same. The only thing that's changing is the response of the device to small changes in the state of the person. So we're going to argue that this energy cost is associated with balance, and we've somehow reduced the effort of balance with this controller. And I think this is the first wearable robotic device that's ever done this. Now, usually people don't fall down when they're walking straight ahead at steady speed. And the thing that causes you to fall down is you get pushed, you get tripped, you slip, or some other big disturbance. So we're also interested in expanding our work into recovery from large disturbances. And I'm working with Hartmut on this environmental emulator, this kind of system where the person's walking along, and unbeknownst to them, at any moment they might step on a piece of ice, or they might get shoved to the side, and then they hopefully get very close to falling down. Maybe sometimes they do fall down, and catch them with the harness, and they make them keep walking. And developing prosthetic knees and exoskeletons for the legs that help recover from those disturbances. Okay, so if you couldn't tell, I think that these universal emulator devices are a really important tool for biomechatronic device design. And the reasons are, you can go from an idea to a test on a person very fast. The type of experiment that you can perform on people is more powerful. You have better experimental design. Particularly, you can design quantitative, you can explore design parameter spaces and develop quantitative design rules that allow you to make rational trade-offs. You can pilot test a product without building it, and you can specialize a device for a particular individual. Over the next 10 to 100 years, I think that these platforms will continue to be really important. In the next 10 or 20 years, we're going to continue to have a type of development where we essentially have these autonomous robots. They do their own thing. You attach them to a person's body, and then hopefully you design them in such a way that the person can make use out of them, right? Hopefully they respond appropriately to their environment. And in these cases, they're big control and design challenges. In about 20 years, I'm hoping that we will have really good neural interfaces, direct neural control of wearable robots. And then the control stuff that we've developed in the next decade or two will just basically be useless. Throw that right out. The person will learn how to control the device and how to use it in all kinds of novel conditions and environments. But we will still need to figure out what types of features the person can exploit best. So what kind of communication works well? Should we be telling the robot to produce a force or a position or velocity, just as a very primitive example? And so I think that these emulators will be important for those processes. Of course, in the long run, biologists and doctors are going to beat us out. And we're just going to regrow amputated limbs, right? Or get gene therapy and completely recover from our strokes. And all this stuff becomes obsolete. But we will still need to try to augment healthy human performance. And probably we'll be trying to do things that we can't even imagine right now with these wearable robotic devices. Big, big augmentation problems. And I think even then, it will be better to have some type of emulator than to spend lots of time designing product-like prototypes. I want to take a second to thank my awesome team here. Josh Caputo is primarily responsible for the universal ankle foot prosthesis emulator design and experiments on push-off work. Rachel Jackson is primarily responsible for the work with the ankle exoskeleton. Myung-Hee Kim is responsible for the work on stability. And Philippe and Roberto did the work on push-off timing modulation. And lots of others have contributed as well. Thanks for your attention. Any questions?
Questions? Comments?
Yeah, go ahead.
So you're implementing a hardware device and software device, right? So there are a lot of problems with this. So can you comment on that? So they're not equivalent.
Can you expand on your
So maybe
question?
for the nominal motion, maybe you can get the same behavior. But during the transients, they're quite different. So you don't have the same bandwidth.
Okay, so let's focus on the last thing you said. So the system that we're using has limited bandwidth. So let's say we wanted to capture behavior that has fundamental frequency characteristics in the order of 50 hertz. We cannot express that behavior with our device. That's true. So let's say we wanted to imitate a hard stop in a prosthetic device. Yes, we can't exactly match what it feels like to slam into a wall. That's true. That will always be true in these kinds of systems. But we can get pretty close. And to give you some points of reference, the closed loop torque bandwidth of human muscle is on the order of 6 hertz. So, we're pretty high compared to that. So, I think the argument that these systems can't express anything, there are things that they can't express, is certainly true. But I think we're certainly, way more versatile than a product-like prototype. Do you buy that?
Yeah, it's good.
Okay. Yeah.
You have to know how your, core density of your joints are capable of this 2 kilowatt AC, how that would compare to like a electro-hydraulic system like used in the Sarcos full body exoskeleton or some of the Boston Dynamics systems?
You mean onboard electrohydraulic?
Not necessarily.
So if you have your actuation system off-board, I think you don't care too much about the whole system. That's it. But maybe you're asking,
Well, I'm talking
you have a
about
hydraulic cylinder on the...
Simulating it running into a wall. So the current system, you just couldn't do that.
Well, okay, well, as long as you have a transmission, that is going to introduce some compliance, whether it's hydraulic or Bowden cable. But let me answer your question two ways. If you put stuff off board, you can have as much power and as big and heavy an actuation system as you want, and the user doesn't really care. In terms of what type of transmission is most effective in these systems, I think that it's hard to beat a Bowden cable because the implications for the end effector, the design elements that need to be in the end effector are just something that you tie the cable to, as opposed to a steel cylinder, right? The other thing is that the conduit itself tends to be more flexible than a hydraulic cylinder, a steel reinforced hydraulic cylinder operating at 1 KSI or 3 KSI. So I think that you're going to find Bowden cables are more effective in these applications. Yeah.
How is the device performance or result will be different with running gait? I think that you got most of the working task with the working gait, and then you have a running gait, you will have more instability lateral side too.
So, yeah, we haven't done any experiments directly studying running. Recently, I think Josh has done some experiments where we try to get at maximum speed. And we accidentally get into running as we're trying to see how fast people can go before they tap out. And the system worked under those conditions, but we haven't done anything careful. Now, when you start to talk about stability and balance, I'm not sure that it's harder to balance side to side during running than it is during walking, actually.
Object-based.
Yeah. So again, most of the research on balance during running has focused on foot placement, right? And certainly these devices don't restrict foot placement, so that's still accessible to you. How much does center of pressure manipulation during running matter? I don't know. And how much does this sort of rebound work modulation matter in running compared to walking? I'm not sure. Maybe we have other people who have done some research in running and spring return stuff. Okay.
So do you think that the device may be used, the same device may be used in the work gait, or do we have to have another optimized design for work gaits?
You mean in terms of end products? I think it's very unlikely that if you optimize the design for running and you optimize another design for walking, that they will look the same, right? And actually, the prosthetic feet that we use for running right now are pretty good, right? Oscar Pistorius qualified for the Olympics because a lot of people characterize the mechanics of the leg during running as this spring-like behavior with half an oscillation. So if you just have a big curvy spring, that kind of does that for you. Walking is a little more complicated, and counterintuitively it can be a little harder from a mechanics standpoint than running. Is it possible to do running and walking in the same device? I think so, but of course you won't do as well. It's a multi-functional device. It won't do as well as one that's optimized for one task or the other. How much performance you lose, I don't know.
Can you talk a little bit more about the human and the loop design as an example from your work, how it iterates through, like what time frames you're looking at?
I'm sorry, I guess I don't quite understand a little more.
This design where you kind of generate your emulator and then you bring it to a human, like what you said, like you can do it with hours, but like when you developed that device that you showed, the second one, what was like the time frame for each step to the other step, and how did you test it?
Oh.
How did you get feedback from the humans, and how did you use that
Oh.
in your next iteration design?
Okay, that's a great question. So let's think about let's go to another slide. So, you know, our work is rife with examples. Here's one. When we first started performing this experiment, we thought, okay, if we go from 0 network up to double the work performed by the ankle, that will be a sufficient range. We're going to find a local minimum that's near the value that people normally produce with the biological ankle joint. That's our hypothesis going in. We performed some pilot tests, and we found actually energy cost is still going down very sharply at double the work. So let's try triple the work. Still going down. Oh, quadruple the work. Still going down. Let's do 5 times the work. And we started having trouble. People were having trouble walking, and we found close to the limits of the system. So there's a case where if we had designed a device that was specialized to produce 2 times the work, we would have been screwed after that first test on a person. But because we've got this very flexible platform, we can do it. Another example is in our timing study. It took us a long time to figure out exactly, first of all, what push-off timing meant, and how to control the device so that it changed the moment when positive power began. And we went through lots of pilot testing. I don't know, maybe 5, 10 rounds of different protocols before we arrived at one that we liked. Or with Exoskeleton, you know, we've tried lots and lots of different assistance regimes with that Exoskeleton. Each one, if we were going to build an autonomous device, a specialized device, we would, you know, it would have different implications. Like if we're just doing torque support at the ankle joint, you'd want to do something with a spring, right? Because if you don't have any network requirements, you can have like a little cam and a spring, and you can follow just the right, you can make it produce just the right torque profile. But that device will never be able to produce net push-off work, right? As an example. Does this make sense? You know what I'm getting? But the big principle is you think you know what the person needs, but you don't. The person is complex, they're tricky, they adapt in all these weird ways. And the most annoying part of the person is their brain. And their central nervous system is very hard to model, it's very hard to anticipate. And so don't spend a lot of time fooling yourself into thinking, I know what's going to work. You don't. Get to that part where you put it on a person and you find out what they actually do as fast as possible.
Any last questions? I'm actually keen to get these devices to give for robot therapy. The last 2 robot humanoids I've worked with, both the knees are way too weak. So I'm also interested in a knee version of this. Thank you very much.